Okay, so yesterday we started our next unit on forces and fields. One of the things we talked quite a bit about was just the idea of how electrons are going to be the big key to this next unit here. Why are electrons the key rather than protons?
They're outside of the...
Yeah, electrons are capable of moving. Why can't protons move?
They're in the nucleus.
Yeah, they're attached to the neutrons in the nucleus, right? So electrons, if you have valence electrons especially, they're capable of transferring. I mean, in chemistry we talk a lot about how valence electrons help make chemical bonds, right? When you're talking about electricity, really, you're talking about electrons running through a wire. So one of the things I talked about yesterday then was the idea of an electroscope. So I was playing around with this a little bit earlier. Let me see if I can turn the video camera so you guys might be able to see. I don't know if this is going to work or not, though. There. So this is the black, I believe it was called ebonite. It's like a hard black plastic. Do you remember what they used to use before they used ebonite? Amber, yeah. And so if I rub amber with fur, I guess. Do you remember what sort of charge it's supposed to give this? Negative charge, yeah. What's happening basically is we're using friction to cause electrons to come from the fur onto the black rod, basically. Right? So two of the terms I want you guys to know then are induction and conduction. Okay. If I move this thing really close to the electroscope, it moved just a little bit. I don't know that you guys could see that all that much. Try this a little better here. Come closer. If I move this thing really close there, you guys can see how the little foil leaves there are moving. Can you guys see that? If not, come closer. Like if you're sitting where I am, you definitely can see. Okay, so I move this thing closer. See how those are separating just slightly? So what's happening when we do that? I'm not actually touching this thing.
The electrons are being pushed to the bottom.
Good, yeah. This thing is negatively charged. Okay. And so this negatively charged object is causing all of the negative electrons that are in here to be pushed as far away as it could possibly be, which means they're getting pushed into those two little gold foil things there, right? As I move it closer, then the electrons are now both in those little foil things. And if they're both negative, negative charges want to repel each other, so it separates just slightly. Does that make sense? So that's negative charge. With induction, okay. Now if I do this with conduction, it means I'm actually going to touch this thing. And what's cool there is now it's staying that way. Right? Now with induction, if I move it there and pull it back, I use the term like temporary dipole. I love that term because I use that in chemistry a lot. So I think it kind of fits here where it only causes it to become positive negative charge until, while it's there. As I pull it back, it goes away, right? But if I actually touch this thing, well, now these things are like permanently separated until I fix it, right? Like, Raj, you asked about grounding yesterday. This would be like grounding the thing. Because what I've just done there is I've allowed all those electrons then to come through me, right? And so I now have a few extra electrons than I used to have. But to be honest, they're probably going to go through me into the chair, into the ground. Like, it's not going to be a major problem. That makes sense? So that's grounding something. Yeah. So this is conduction, where we're actually like conducting a charge from this object straight through to those guys. And that's going to leave a permanent negative charge. Well, I mean, as permanent as I want it to be, right? If I touch the thing, obviously it's going to change. Gotta do this more, because that didn't separate nearly as much as I'd like it to. Yeah, so this is induction. That is conduction. It's not separating nearly as far as it was the last time. Yeah. There you go. Okay. So now I've given this thing a negative charge. This is hopefully going to work, because it wasn't working a few minutes ago. This is a glass rod, I think. And this is silk. You guys remember what happens when silk and glass are rubbed friction-wise?
Positive.
It's a positive charge, which means I'm taking the silk and putting positives on the rod, right? You can't put positives onto something, right?
Right. You're taking the negatives away.
Right, I'm taking the negatives away. So what's happening here is the silk now should be negative and the rod should be positive. I mean, you can almost hear this. I don't know if you can hear like the friction on there. Can you guys hear that from there? Okay, I can hear it. I promise you, I can hear it. I mean, you can hear like those little, like, if you ever have like a static electricity shock, right? Like you can hear the snap. So hopefully this thing is now positive. Okay, so if this thing is positive and it comes close to something negative, could you guys see that a little bit?
Yeah.
It was actually going in, just slightly. This one wasn't working as well as I wanted to. If this guy's positive and that guy's negative, what's happening is all of those negative electrons are now being resucked back up into the rod here, then allowing the leads to then come back to their normal positions. It wasn't working quite as well as I was hoping for, but let's see if we can get it to work a little bit better here. You guys see that? So those are negative, this is positive. Electrons are being sucked back up to the top here by induction. That's conduction. You get the difference there? Okay, so that's more or less like the basics of yesterday. I need you guys to know those terms. You should also know about like superconductors, semiconductors, conductors, insulators. Just know those terms. I have no clue how they're going to assess you on that. Does that make sense? I mean, it's a definition. You know, they could give you an example of something and then say which of these four things best fits. So I'll try to find examples of what they've done in the past, but it's going to be pretty open-ended for theory questions. So make sure you know your definitions. Make sure you've read through the textbook section at least once. That's really worth it. I think what I'm going to try to do is find other textbooks and photocopy some pages for you to read so that you have lots of different readings to do, because that's one of the best ways of learning a lot of this theory stuff is just to read about it. Does that work? Okay, that being said, today's topic is the like big math-based section for this unit. We're not going to do much math after this. Like we'll have a few formulas here and there, but this will be the big math day. So, it is. It's right behind you. You're welcome. Okay, so I'm just going to read off my notes to start here. You guys probably know this. If you have like charges, they will repel each other, and unlike charges will attract. I think I mentioned this yesterday. The symbol Q, either lowercase q or uppercase Q, stands for like charges. Did I tell you guys this yesterday? So, the problem is that capital Q sometimes gets used in chemistry for heat, so that's kind of annoying. So if you have, like, say, negative and positive, they should attract each other. And if you have negative and negative, they should repel each other. Here's a keyword. I bolded this. Physicists have known this for probably thousands of years, since ancient Greece. They've recognized the fact that charges can either attract or repel. But they have no way of quantifying. What does quantifying mean? Yeah, put a number to it. Right? If electrostatics are either repelling each other or attracting each other, the word we need to talk about here is F. There's some sort of force going on here, a force being measured in newtons. And so, although scientists have known about charges for years, it wasn't until, I think I might have a date on here. No, I didn't put the date on here. I believe it's like the 17 or 1800s, when we finally actually found a way to like quantify, put a number towards how much force these things actually have. Could one of you guys grab the door? So, two things though that hopefully make sense just intuitively to you guys. First of all, the more the charges, the more the attraction and repulsion. Does that make sense? Like if I have a little bit here and a little bit here, it's going to cause a little bit of attraction. But if I have a lot of charge and a lot of charge, that's going to have more attraction. Does that make sense? And then the second thing is, the further away the distance between these things, the less there should be. So if you have two charges right here, you're going to have a lot of force between them. But if they're way out here, is there still going to be some force? Sure, but will it be as strong? Probably not. This might seem really similar to something else we talked about. Gravity, yeah. It's actually really similar to gravity. Before, do you guys remember the term the Cavendish experiment? It was how Henry Cavendish figured out a way to find that capital G constant. Charles Coulomb was actually doing the exact same thing, but with charges instead. Basic idea is he made this charge be positive and this charge be positive. And if they're both positive, they're going to want to repel each other. Does that make sense? And so that was going to cause this little wire thing to rotate that way. And I'm guessing he probably made, like, say, this one negative and this one negative, which would then cause them to want to repel each other. Now, I believe these ones right here were like fixed in place, so they couldn't move. And then these ones were able to rotate on a wire. Right? And so then he was able to figure out a formula. One thing I learned when I was researching this yesterday is we talked about the whole how do you calculate that amount of twist. And what I read here is that Coulomb measured how much force it was going to take to twist the wire. So I imagine like he twisted the wire 1 degree and said, okay, that's 1 newton of force. He twisted the wire 2 degrees, said, okay, that's 2 newtons of force. Twisted the wire 10 degrees and said that's however many newtons of force. Does that make sense? And then when he did his experiment, then once he actually had these things repel each other, but depending on how many like degrees like of twist there would be, like if normally he was supposed to be right here, but then it moved to here, he would measure the angle right there, and whatever angle it was, that must be how much force there was applied. So, anyways, long story short, here is Coulomb's law. And this is on your data sheet. It's going to look really familiar. Yeah, we call that one the universal gravitation formula. I have it on, I think, the next slide here. This is the universal gravitation formula. So a force is equal to 2 different objects times together, divide by their distance, but then you also have to have some sort of constant in the formula. Well, it's the exact same thing for this is Coulomb's law. 2 different things right here. So these are the 2 charges. So charges. Charges are measured in something called a Coulomb, by the way. Capital C. Did I mention that yesterday? No. Okay. Capital C stands for Coulomb, at least in this context here. And that's a measure of how much charge there is. So you need 2 different charges, obviously. R. Yeah, like distance between them. Distance. And then K is kind of like capital G. It's a constant that, in this case, Coulomb solved for. And so this is on your data booklet somewhere. I pulled this right out of there. It's 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. Can you guys find that on one of the sheets there, where it's got like all the different important values, so you can pick it off out of that listed stuff there? You guys can find that? Yeah. This probably won't seem all that difficult then, because we did the exact same thing, only with gravity, but now we're doing it with electrostatic forces. So, I have a couple of notes here before I try some examples. First thing I want to point out is here are the 2 different constants, so K and G. One of them is way bigger than the other one. This one is a times 10 to the 9, meaning you have to add like 9 zeros afterwards. This one is times 10 to the minus 11, meaning there have to be like 11 zeros before the number. So this number is way bigger than this number here. There's actually a reason for that. Gravitational forces are actually way lower than electrostatic forces. That might seem weird. You're thinking maybe, well, hang on, isn't gravity like a really strong force? But on like a normal scale, Earth is so massive that it actually has a fairly large field. Okay? But like, let's say we're talking about just 2 random objects, like me and this water bottle right here. Is there a lot of gravitational force between me and the water bottle? No. Now, if it's the Earth and the water bottle, yeah, it's a bit different. But like on like a pretty average comparable level, there's actually not going to be that much gravitational force. That being said, electrostatic forces, you might have seen like someone like rub a balloon on their head and then stick it to the wall. You ever seen that example before? Well, that's electrostatic forces causing these things to stick together, right? Even the forces you see in this little thing right here, they're actually considerably stronger than, you know, the force between me and my water bottle. Does that make sense? So, second note here, gravitational forces are always of attraction. Supposedly, you know, me and my water bottle are, you know, being sucked together. Not very strong, obviously, but a little bit. Whereas electrostatic forces, those can be attract or repel, which is kind of cool. Does that make sense as well? Huh. One last thought before, well, maybe two last thoughts before we do some examples with this, with some calculator math. The type of charge is irrelevant. Okay, when you use the formula for like F equals K Q1 Q2 over R squared, that formula there, don't worry about plugging in positives or negatives. For you guys in my Chem 30 class, it's going to be very similar to when we're doing entropy or enthalpy. And so we're going to throw a negative or a positive on when we're done. Okay? Let's say both of the charges are positive. They're going to repel each other, which means the force is going to be pushing things away. That makes sense? So when we're done, we'll figure out which direction to make forces go. If one was positive, one is negative, then they'll attract each other. But again, don't worry about the positive negative thing until we're done, then figure out a direction. One more thought here. I want to talk a bit about coulombs before we do this. Coulombs is a measure of electrons. I believe I've taught all of you now the concept of a mole. You guys remember what a mole is for chemistry? Like 1 mole equals 6.02 times 10 to the 23 like atoms. Okay. Well, a coulomb is basically a whole bunch of electrons. Rather than counting electrons one at a time, which is kind of ridiculous, here's the ratio. 1 coulomb is this many electrons. So you're just counting a whole bunch of them at once. This number right here is not on your data sheet. No, I'm going to show you how to solve for it if you ever need to. I talked with Forrester at length yesterday because I wanted to pick his brain about what they might test you on. And he told me that it's very likely that what they might ask you to do is solve for coulombs and then put it into electrons, which would be really similar in chemistry to you have to solve for moles and then convert it to like grams or something like that.
Sure. Do you have an air mouse?
I don't know. Sorry. Let me say that one more time because that's really key. What you might be asked to do is solve for coulombs, like solve for Q, and then after you're done solving for Q, then convert it to like total number of electrons. And that would be kind of similar in chemistry to I ask you to solve for moles. And then when you're done, I ask you to convert it to say like grams, like just one more step. So, okay, anyways, here's how you find this number on a diploma if you don't memorize it. Okay. This is given to you. It's called the elementary charge. It says that 1 electron is like a fraction of a coulomb, like 1.6 times 10 to the minus 19 of a coulomb. Okay, so this is given to you. So if you want to work with that, it would look something like this. 1 coulomb multiplied by 1 electron per 1.60 times 10 to the minus 19 coulombs. You guys see how the coulomb unit is going to cancel? So the coulombs will cancel. And if you do 1 times 1, which is kind of pointless, divide by the 1.60 times 10 to the minus 19, that should yield, I hope, that number right there. Either that or I really screwed up yesterday. So it's kind of like molar mass in chemistry. It's kind of like if I give you 5 grams and you're multiplying by a mole for every 40.00 grams, canceling that out. Okay. This number right here basically tells you a ratio of coulombs to electrons. But normally we don't want to know things 1 electron at a time, because like 1 electron is pretty small, right? So usually we want to measure things in coulombs. So this might actually be the more useful ratio for you. So it may be worthwhile just to write this down, and then on the diploma, as need be, just resolve for that number. Does that make sense? Okay, let's try some examples then. Oh, actually, no, one more thought here. I have all these things that I need to remind myself not to forget. Do you guys know the units MC or like the funny little UC? Do you guys remember what those mean? M stands for milli. And I can't draw the U the way that it's supposed to be drawn. It's supposed to be drawn like this. Do you guys know what that prefix is? Micro, yeah. So they're on your data table as like times 10 to the minus 3, I think, and times 10 to the minus 6. Often, you're not going to be working in full coulombs. You're going to be working in like milli or micro coulombs. because like a full Coulomb is actually a lot of electrons. And everyday life stuff is not usually actually a full Coulomb. That makes sense? I was reading up on this. Apparently like 1 or 2 coulombs would be like a lightning strike. So most of the stuff that we work with is going to be like a part of a Coulomb. Okay. Another note here, many objects actually have this many electrons, but they're balanced out by protons. So a Coulomb is not actually how many electrons there are total. A Coulomb is like how many extra electrons there are. Does that make sense? Because, I mean, there's going to be millions upon billions of electrons running through all of this stuff here. But coulombs are going to be like, if you had 5 and 5, that would be no coulombs. But if you had 5 and 6, now there's actually a difference between like protons and neutrons, or protons and electrons. Does that make sense?
So it's kind of like it's charge of negative, or measure of negative charge then?
Yeah, and you can actually do coulombs in measures of positive charge, which would basically be how many extra protons there are compared to electrons that have been lost. So, okay, all that being said, let's try some examples now. So, first one here. You've got an object with a charge of -2 microcoulombs. So negative, meaning that there's going to be more electrons than protons. So here's an object that's -2 microcoulombs. And there's another object over here that's +3 microcoulombs. We want to figure out the electrostatic force between them. So this guy's negative, this guy's positive. When we use these numbers in our formula, ignore the negative positive part, that's not relevant. But what's going to happen? Are these objects going to come together or separate? Good, okay. We also know the distance is 0.15 meters. Okay, so here's how this will look. To find electrostatic force, you're going to need K, Q1, Q2, all over R squared. So, anybody know what K is off the top of their head yet? Or at least can go look it up.
8.99
Okay, 8.99 times 10 to the 9. Units for that? Okay. Now, based on this thing having a unit of coulombs, this guy right here as a microcoulomb, we can't leave them as microcoulombs, unfortunately. That makes sense? So we are going to have to convert. So what's a microcoulomb? Is it times 10 to the -6? So 2 times 10 to the -6, 3 times 10 to the -6. That means your coulombs can cancel. And then on the bottom, we need our distance or radius in meters. Fortunately, this one was in meters, though. So then the meters can cancel. Calculator. Times 2.0 times 10 to the power of -6 times 3/4 times 10 to the power of -6 squared. Anyone get an answer? What'd you get?
Like 0.3596?
No, I got 2.4. 8.99 times 10 to the 9. Yeah, that 0.15 on the bottom should be squared.
What did you get, Sean?
I got 2.3973 repeated.
Yeah, I got that.
Okay, good. This number right here. That one right there. Lisa, this number here. Okay, so in terms of sig digs then, we still have to do that obviously. So it looks like 2. Oops. So let's call this 2.4 newtons.
Why did you show? Isn't it to the power of power 12, or did I?
Like you have 2.39, but you have to the power of 12?
I have that, and it's like repeated to me as.
I don't have that. I just got this rid of 2.4.
But it's micro.
number, but not the same exponent. Okay, one last thought. Direction will be important. I can really envision on the diploma exam, they give you the answer for like A as 2.4 and the answer for B is also 2.4, but then they might make the difference on the two of them be like direction. Does that make sense? So for this one right here, like the direction of the force will be like together. That might be a good way of putting it. Like they're getting sucked in together because they have the same charges. Often they'll phrase it, so they'll ask like, what is the charge or what is the force on like say one of them? So you might say, well, this guy is getting a force to like the left or to the right. Does that make sense? If these guys are both the same charge, I might say the force is pushing them up, away, apart, something like that would work.
So can you find individual then? Like
Well, so really what I could say here is that this guy right here is being pulled this way by 2.4 newtons. Simultaneously, this guy right here is also being pulled this way by 2.4 newtons. So like what they might ask you is, what is the force on this guy right here? And so you'd say this guy right here is being pulled 2.4 newtons to the left. Whereas this guy is being pulled 2.4 newtons to the right.
Is that an average because like the one has a different charge than the other? Like, do you know what I mean? Or is it just
It's
that
no different though than like gravity,
Okay.
right? Where you and the Earth, I mean, you both have different masses, like
Yeah.
vastly different masses, right? But you're being pulled down towards the Earth. The Earth is technically being pulled up towards you, but really you're not going to feel the Earth being pulled towards you. You're going to feel yourself getting pulled to the Earth. Does that make sense? Okay, let's try another one. Only here we're going to use the formula like backwards and solve for a different variable. So I'm going to give you a charge of 1.8 times 10 to the minus 6 coulombs. So here, let's go positive, I guess. And then 2.4 times 10 to the minus 6 coulombs. But here, I'm not going to tell you what that distance is. I think you guys could rearrange the formula then and solve for r instead.
Yeah.
Okay, give it a try. I'll give you a head start then. So rather than giving you the distance, I'll give you a newtons instead. .99 times 10 to the 9. And then positive 9, not negative 9 for that exponent. When you're done, don't forget the square root. Hey guys.
Hello. Yogurts, bananas, and oranges.
I'll have yogurt actually. I got 4.2. I think I heard you guys say you got 4.2. What are the units for that going to be? Meters, yeah. Yeah, I didn't write my units all the way through here, but this 8.99 was what, newtons, meters squared over coulombs squared. So meters is going to be your units when you're finished here. Well, no.
Because I got
minus 6 as well. We'll do that. We'll take that and divide by 2.2 times 10 to the power of -3. And then we'll square it. There you go. Just a mistype. Alright. Any questions or issues on that for anybody else? You guys can handle this?
Yeah.
Cool. Okay. Chances are, from what I understand, like I said, I did a lot of talking with Forrester about what to expect. Chances are you're not actually going to be asked like a question that simple. They're going to make, yes, they're going to give you at least 3 different charges, possibly more, and they're going to ask you to find like the net force acting on a charge. So on this question here, I want to ask you guys to find the net force acting on the negative charge. Okay. So there's 2 different forces we have to find. There's a force between these objects, and then there's also a force between these objects. Okay. Which way is the negative charge being pulled, I guess, in this interaction right here? It's being pulled that way, right? Does that make sense? But then in this interaction right here, the negative charge is being pulled the other way. So what we're going to do is twice the work, and when we're done, we're going to take our 2 forces and subtract them. It's kind of like a tug of war. Does that make sense? Where red is trying to pull blue. Let me try another color here. Getting a little busy now. Red is trying to pull blue this way. This red is trying to pull that blue this way. So we want to figure out what's going to happen to blue when it's done. The way I was told to maybe describe it is, imagine that this guy is stuck, this guy is stuck, but the middle one is able to move. So it could slide one way or the other. We want to figure out which way is it going to slide. Does that make sense?
Depending on which force is bigger?
Yeah, depending on which force is bigger, right? So if the force between these 2 is bigger than the force between these 2, he'll go that way.
So say he goes to the right, you just subtract the 2 forces?
Yes.
Okay.
Yeah. So, I mean, basically just do the same work we were doing, only do it twice. So.
Is that a 10 to the -8?
I believe those are all 6s.
Okay.
Let's go with 6s just so we're all on the same page. So those are all times 10 to the -6.
Oh, yeah.
Yeah. Let's go 6. 6.
Is that 1.65 meters?
That's 1.6. Let's go 1.65. Yeah, that didn't show up very well, did it? Let's see. 3.30 minus 1.65 is also 1.65 apparently. So both of these are 1.65s. Is that 1.65 centimeters?
Yeah.
1, 2. No, too many zeros.
Yeah, 1 plus.
I have too many zeros there. Let me try that again. 0.0165. Like that. That's 1.65, yeah. 8.99 times 10 to the 9 times 1 times 10 to the -6 times 2.1 times 10 to the -6. Whoops, that should be -6. Times 10 to the power of 9 times 1 times 10 to the power of -6 times 2.1 times 10 to the power of -6. Divided by 0.0165 squared. Okay, so I found between these 2 guys right here, I'm going to call that F1, just to label them. I got a value of 69.344 newtons.
Yep.
And just do the exact same thing for the other 2 guys. let's see, that's a 2.1 times 10 to the minus 6. Is that a 1.5 right there?
Yeah, that's why I have 1.5.
1.5? Okay. And then this will also be over 0.0165 squared.
And then you practice the 34.
I got all the same numbers, but just less sig digs. I mean, like the point.
This one should be 0.0165, not 0.165. 1.65 divided by 100 is 0. You're missing a 0 after your. That should be 0.
I got 104 for the other set of newtons.
That's what I got.
You guys got 104 as well? Your calculator.
This, you have to subtract this one. This is.
And don't do the negative. I mean, I guess you can, but the negative's not really relevant. Wait, so one last thought here then. This force right here pulling this way is 104 basically. This force right here is about 69. So subtracting those numbers, minus, what was that, 69.344 with what, 2 sig digs? 3 sig digs. I got 34.7 newtons when I subtract them. 34.7 newtons. And then in terms of direction, I'd say it's getting pulled that way. So, sure, right, based on this perspective. Does that make sense? Cool. Okay, I've got 2 more examples I think we need to do. But these I'm going to leave till after we take a break because these are going to take a little bit longer, sadly. The big change for these ones is these are no longer linear. It's kind of like momentum. We did some momentum examples where everything just hits in a nice straight x direction. But it is possible, and very likely, apparently, that you're going to be asked to do stuff in both the x and y direction. Yeah, good times, eh? So go take a 5-minute break, and when you come back, we'll finish these ones off. Okay, guys, I'm going to keep going here with these last 2 examples. Or maybe I won't, actually, because I just lost the video chat. What just happened? Alright, I've only got half an hour left, so I'm just going to start. I know these guys are waiting here, so hopefully they can still see what I'm doing at the least. Okay, so our goal now is to work on x and y direction. So all of these, it doesn't say a negative in front, so let's assume if it doesn't have a negative, they're all positive charges. So what's going to happen to this red one right here? Where's it going to get pushed to? Yeah, it's going to get pushed like down in this direction. Does that make sense? Ultimately, there's going to be like a resultant triangle out of it. Oh, good, you guys are back. Where this thing right here is going to push him that way. So this y1 right here is going to be like the same as this y1 right there. Sean.
Is this then assuming that Q1 and Q3 are stationary?
Yeah, that's usually the assumption I've been told we should make, is that these guys are considered stationary and this guy is capable of moving. Because really, like, what would happen is this guy would get pushed this way, this guy would get pushed back, this guy would get pushed back. So, then these guys right here, this is going to cause this one to go that way, so I'll call that, like, say, x1. And so that'll be x1 right there. So really, again, we're just doing this twice, but when we're done to find the net force, we're gonna have to find like a hypotenuse resultant when we're finished, and we're gonna need an angle. Does that make sense? Okay, so let's give it a try. To find y1, that's going to be 8.99, 10 to the 9, 2 times 1. By the way, 2 coulombs and 1 coulomb are probably not realistic in everyday life scenarios, but so be it. Yeah. It's happening. Deal with it. 3 squared. Yeah, it's gonna be a pretty big number, right? Okay, so I got 1.997 times 10 to the, count this out, 3, 6, 9 newtons. You guys get the same thing there? 1.99 times 10 to the 9 newtons. Okay. And that was y1. Yeah, that was y1. And then for x1, more or less the same thing. Oh wait, no, this will be not 2. That'll be a 4 times 1 over 4 squared. Sorry, that's a little bit of a mess there. So 4 over 4 squared. And then here I got 2.2475 times 10 to the 3, 6, 9. Yeah. You guys got the same thing? Okay. So, end of the day then, that's one side. This is the other side. We've been doing this a lot over the last, 7, 8 months we've been together here. So, hypotenuse this thing to find the actual resultant, and inverse tan to find some sort of angle. So, that squared plus 7, 7, 7, 7, 7, 7. 8. Squared. So I got a hypotenuse. This is a mess here. Answer. I got 3 point. What do I get for sig digs? Just 2? 3.0 times 10 to the. Probably a 9 again. 3, 6, 9. 9 newtons. And I got an angle of 48 degrees.
Yeah, I got 42.
Did I do mine backwards? Oh, I did too. I solved for this angle. That's why I got 48. So yeah, you guys should be right. That'd be 42 degrees. And then if this was like north, south, east, west, maybe you could say it's 42 degrees south of, no, that's west over there.
If you write like west 42 degrees south.
That'll work. Yeah, you could do west, then 42 degrees to the south. That's valid. Long story short, this angle here is 42 degrees. So long as you know that and you can answer the question however they choose to write the angle, you're probably good. Does that make sense? Okay. It's not that bad. That one's not bad. This next one here is going to look almost the exact same, but I've made one twist. Rather than it being this guy that we're looking for, it's actually this one down here that we're trying to consider how things push. That makes sense? So a positive and a positive will repel each other, right? Meaning that this C is going to get pushed down by B. But A to C right here, well, this is negative and that's positive. So he's going to be pulled one direction, but then like pulled back the other direction at a bit of an angle.
So then his like resultant is not like is there gonna be a resultant?
Well, there should be a resultant, yeah.
But it's not ready.
Might not be, no. Do you guys see how this question is different from last then? I mean, it looks the same when you start, but it's totally gonna screw things up.
Draw your angle then.
Okay.
Bring your triangle
Okay, can I do the triangle thing second? First I want to do the easiest one of the two, which is let's find this force like y right here. I'll call it Fy1 because that one's easy to solve for, hopefully. So Fy1 will be equal to your 899. Let's see, you've got a 1.8 times 10 to the minus 6. You've got a 1.5 times 10 to the minus 6. And it's all over 3 times 10 to the minus 2 squared. Just hear calculator buttons just furiously tapping away, right? Okay, good. That's what I got to. Need to put this on your Ask app. Or no, what's the one you guys do? The Trivia Crack. That's the one. Trivia Crack. What's the time limit on Trivia Crack? What do you get? 30 seconds?
Yeah. Is there a person like this on there?
Furiously type away.
I was like, I don't know.
Okay, is everyone okay with getting that one? That one's probably the easiest of the two. So that's 2697. Okay. The one that's going off in the corner, that's going to be a bit more of a struggle. And so what we're going to need to do is draw like a triangle here. Let me redraw this a little nicer. And the number that we're actually going to solve for is going to be the hypotenuse. And so what we're going to have to do then is break it up into x and y. So this will be fx1. And this, well, let's call it 2 actually. And this will be Fy2. That makes sense? But first I actually have to solve for like the F hypotenuse 2. So I actually have to solve for this first and then use that to break it up into these different pieces here.
How would you find the hypotenuse?
Okay, well, we know this guy's charge. So like if I want to do the hypotenuse one, I know 899. Times 10 to the 9. I know the charge on A is 210, 10 to the minus 6. I know the charge down here on C is 1.8 times 10 to the minus 6. The problem is I don't know the distance from here to there.
Have you tried it with like the hypotenuse of the distance between
Good.
3 and the 2?
Yeah, what you really have is like a right angle triangle. Like here. And so this is a 3 and that is a 2, basically. So we should be able to find this distance right here by doing like another Pythagoras' theorem. So like square root 2 times 10 to the minus 2 squared plus 3 times 10 to the minus 2 squared. Probably. Yeah, I ended up with 3.6 times 10 to the minus 2, I think it was. So that's the hypotenuse distance. That makes sense? So using this number down here now, we can find the hypotenuse force, which we're then going to have to take the hypotenuse force and, just like with momentum, break it up into an x and a y. But first I got to find this value. So 8.99 times 10 to the power of 9 times 2. What is that? Is that a 1.5? I can't even write neatly. 1 0. What's a 0? 1 0 times 10 to the power of minus 6 is 1.8 times 10 to the power of minus 6 divided by 3.6 times 10 to the power of minus 2 squared.
I rounded that because it's an engineering too. I just left that as that.
Did you get my 6 for 1?
Yeah.
Actually, I used the 3.6 right there. I should have used the 3.60555 number.
I just used,
Okay, yeah, mine's wrong because I didn't use the actual, that 3.6 number.
What did you
26.1401.
Okay, go back up here. Divided by... my calculator doesn't go back up. That 3.6 number, what was that number? Does anyone have it nearby?
0.0360555.128.
Thank you. 0.036? I got 26.1.
Yeah.
26.1. I got like 407, something like that, newtons. Is that what you got? Okay. Okay, next thing we got to do then is if this number right here is the hypotenuse is basically 26 newtons, we have to break it up into an x and a y direction. To do that, we need to know an angle. We don't have an angle yet.
Yeah. Oh, but we could find the angle of like the other triangle, and then would it be like the
Opposite.
Sure, like why don't I find this angle right here by like inverse tanning. And if I find this angle right here, that angle would actually be the same angle down here. That makes sense? So I'm going to inverse tan. From this guy here, the opposite would be 3 times 10 to the minus 2. The adjacent would be 2 times 10 to the minus 2. I got 56 degrees basically.
Yep.
So if this is 56 degrees, then this guy right here would have been 34? Which means this guy back here is 56 degrees again. Did you guys get what I got there?
Okay.
You got it, Heather?
Yeah.
Perfect. Sorry this is a mess. I hope you guys can still follow. Okay, so let me redraw this a little nicer then. This triangle right here has a hypotenuse of basically 26 newtons, has an angle of about 56 degrees, and what we need to do is find the x and y values for that triangle.
Yeah, why do we need those guys?
Okay, so going back to where we were starting here, this guy is pulling down right here. This guy is going to pull up right here. We're going to take this number right here and this number right here, and we're going to subtract them to figure out how much y direction there is. And then this guy right here has an x direction. He's going to be the only x direction happening. And so we're going to find like a total in the y direction. We're going to find a total in the x direction. And then one more time, we're going to do a hypotenuse to try to find a c squared. Does that make sense?
Is our FY1 from B to C?
Our FY1 is going to be from
Like the first
this one right here was from B to C, yeah.
Okay.
That's why I figured that one out first, because that was the easiest one. So what I'm hoping to do now is find FY2 and FX2 by using sine and cosine. So this guy is going to be 26.1407 times the sine of 56. And this one's going to be the 26.1407 times the cosine of 56. So I got 21 and 14-ish. Yes?
Yeah.
Okay. We're almost done. This is a pretty crazy question, eh? There's a lot happening here. Okay, let me see that I can try to draw this one more time as to what we just finally solved for. It took a long time, but here's what we found. This sphere right here is going to get pushed down we know how far down it's getting pushed in terms of newtons. Now, we had to find a hypotenuse between these guys, and that was a challenge on its own. But this hypotenuse can get broken down into the fact that he's getting pulled up and he's getting pulled over. So in your y direction, this value right here is pulling up, and this value right here is pulling down. So what is the sum of your y direction values? So in the y direction, it was 2175, but then this one was 2697. So we're going to need to subtract those two numbers because this one's pulling down and this one's pulling up. So, whoops. Okay, and which way though, up or down? Okay. So then I'm just going to try to organize this neatly. So in the y direction, it was what, about 2697 minus your 2175. So that gave you 5 point what? Okay. Newtons down. What about the x direction? Yeah, it's just that 14. Because really there was nothing else going side to side. So this one is just the 14.50. And that one I believe was going, what is that, left? So last step, like we've done so many times. Someone's going down, someone's going right. This number here is 522. This number is 415, whatever. Hopefully you get the point. Find the resultant, and then find an angle.
Would the angle be like east of what? Of south?
Yeah, if we draw it like this, it would be east of south. Or no, west of south. West would be that way. East is the other way. So let's see, that number squared plus 5.22 squared. Square root. So I got a resultant of, my sig digs, 2? 3. 3 sig digs. Yeah, I got 15.4. So that's your resultant force. And then 5.22. I might have a different number of sig digs here because my calculator I didn't keep track of very well all along here, but I got about 70 degrees. I got 70.2, but I have a feeling that I didn't keep enough decimal places. Oh, okay. Okay, so 15.4 newtons, and then you could say that this was going 70.2 degrees west of south. Or you could say like south goes 70.2 degrees west. Those are valid options. That last one's the worst, eh? Like the two-dimensional one where it's there's two of them and you're looking for just the one in the middle, that one's not bad. But the two-dimensional one where you're going this way, and you're looking for the one on the edge, that one sucks. Because first you got to find the one that's just a straight line. And then you've got to find the hypotenuse. So you actually have to find the hypotenuse. You have to find the hypotenuse force. You then have to break the hypotenuse force up into x and y. And then you have to sum them all together. And then you have to refine the hypotenuse again. That's a lot of work. Alright. Any questions?
Would it have been not relevant for us to calculate the distance or the force between A and B? Because they were like attracted to each other, right?
I asked that question too. I wanted to confirm on that. Yes, these guys are attracted to each other, but the general way this question, as far as I understand, is going to be phrased is that this guy is locked in place, this guy is locked in place, and this guy is free to move. So yes, even though these guys are attracted to each other, that's not relevant to the scope of this guy's being able to move. Because I agree, because like really what would happen is this guy's going to get pulled, like he's going to get pushed that way, he's going to get pulled that way, but like these guys are going to go in towards each other too. So, but these guys are going to be fixed in place, and this guy is able to move.
Yeah.
I know.
That was a long question.
It was.
From how to do that.
Okay, any questions?
They throw that on us.
As far as I understand, yes. Yeah. Okay, for today and tomorrow, I'm not going to do a lesson tomorrow. But here's some things to take a look at. Please read through this set of chapter pages, just for some of the theory stuff. And you're going to want to practice a few questions like this. You probably use these skills though. Like we did this in our dynamics unit, in our kinematics unit, and momentum. Like we've been working on these skills for a long time. Not exactly the same way, but very similar triangle-y type stuff. You know what I mean? So if you get the hang of how to use that formula, you'll probably be fine. But here's 4 or 5 questions to work on. Does that sound good? So tomorrow's a work day, and then we'll take a week off. So we have finished 2 out of 9 chapters we have to cover, just so you guys know. We have to cover 9 chapters in our textbook. We've now covered 2 of them.
You know, it
So.
doesn't seem that accomplishing right now. It just seems like, oh wow, I have 7 more.
Well, that's